Good afternoon Europe, good morning America, and good evening Asia. Welcome you all on the second webinar series of this year, of the 2026. As I heard before from my team, we are already having 23rd series of the webinars organized by Elmarco since the beginning, which is a great number. So let me introduce the topic of today. Today's topic will be tailoring composite performance at the nanoscale. This is quite interesting topic of interpreter Dr. Vasileios Drakonakis from Cyprus. I will talk details about Vassilis later in my presentation. But just to highlight that this is very interesting topic because of the rather new application in combination with nanofibers. You know, we've been usually hearing nanofibers in connecting with filtration, separation, membranes, medical. But today we will hear quite impressive talk of application in composite. So I think it will be very interesting. Before that, I like to also highlight some topics which are being prepared for the next period. So we have a speaker of September, Mr. Václav Houska from a Czech company. He will be talking about visible light activated antimicrobial nanofibers for medical dressing. And we have other talks coming in October, November, also related to biomedical application. So as usual, I like to say some words, just small talk about Elmarco. What does Elmarco do? So Elmarco does deliver equipment for making nanofibers. I must say that we deliver not only equipment, but we deliver the whole entire key solution for making nanofibrous materials. We are collaborating with experts and with customers. They are bringing the product into the market, and we are really helping them to get the product on the market as fast as possible by collaborating in maybe additional some peripherals, talking about downstream process, helping them basically establish the whole technology. That's the portfolio of the machinery that we are making, producing, installing, delivering, and servicing. We're starting from a small laboratory scale equipment, which are mainly delivered to research institutions and universities. Then we're going to a little bit bigger machines. We call it pilot scale technologies, which are a half-meter width technology, which producing reasonable, let's say, volume of material. And going through the 1 meter wide line, already talking about the really industrial scale production, ending up with 1.6, and we can go even to 2 and 2.5 meter wide machinery. Elmarco in numbers. So we are in the market already for 25 years, and we are still learning, although we really gain a lot of, very valuable experience in electrospinning, combination, different polymers, different substrates. So our knowledge is enormous, and we are ready to share. We are ready to help you to develop your own product and to bring your product to the market. We are pretty stable in number of employees, 85. That's the intermediate size of company, and we are occupying more than 3,000 square meters of R&D center. Everything located in Liberec, Czech Republic. As you can see from the map, so headquarters, as I mentioned, is located in Liberec, Czech Republic, beautiful country in the middle of Europe. You're very welcome to visit. So we have everything located here. It means the R&D, assembly, logistic. We have design team. We have a chemistry team. We have experts. Pretty much everybody is working from this location. Although we are really collaborating very closely to our sales representatives, which are spread all over the world. But we have very important strategic partners, namely in Italy, because Italy is becoming very important market for us. We have a colleague of us that is located now in the US that helping to develop the US market. We have very new Tokyo branch office open up this year in Japan, which is also very important strategic place, location for us. We have a lot of customers from that area, and we have a strategic partner for Hong Kong, cover pretty much China land and Hong Kong area. So how does the Nanospider technology works? So we are different from the needle-based spinning. Of course, we are needle-less electrospinning experts. So we're working with wire. So wire is basically the electrode where the solution is deposited on the wire, and by implementing high voltage, the nanofibers are generated. Massive stream of fibers is coming upwards, where they are collected on the moving substrate, which is kind of supporting layer, and nanofibers are forming a form of, let's say, 2D structure layer, which can be in different thickness. Faster you go, thinner layer of material you make. And then you can basically verify your fiber thickness, your thickness of the entire layer. You can play with the pore sizes, and everything is possible with our technology. How do we work with customers? And I actually talked about it last time already, but I want to really say it again, because we now more than ever work very close to customers with closing joint development projects. And why is that? Because we are now realizing that we cannot definitely investigate or develop the product by ourselves. We always need a partner. And this way, it's proven that it's a very effective, very efficient way of how you can accelerate development and bring the product to the market much faster. So we work closely with customer, closing contract, either contract manufacturing, sometimes for the short-term production, but mostly development projects. We also offer processes as a part of the service that we offer. We call it sampling process. This sampling process enables you to verify your product by saying us your requirements. We will produce the requested number of meters or kilometers of material delivered to you on a roll, and you will analyze it and come back with us with some feedback. We will talk about it and then do some adjustment if necessary and continue in this way. We have very nice sample books developed or established or designed this year. It's kind of new at Elmarco. And we have an option even now to have the sample books online. These sample books basically demonstrate the portfolio or the main used, let's say, combination of polymers and substrates for each application. And if you want to have the list, such a list of samples that we are ready to ship to you, you may ask us via the address sales@elmarco.com. And we will provide you this online version of sample book. And once you select your most wanted sample, we will ship it to you in real. All right, so that's enough from my side, and I will shortly give a word to Vassilis. Maybe just to introduce him a little bit. I know him for quite some time because we started collaboration many years ago when they purchased our equipment. Of course, they're using pilot scale production equipment for their development and production. So Vassilis has a diploma in mechanical and aeronautical engineering from the University of Patras, and he gained his PhD in industrial processing and manufacturing engineering from the University of Texas in Arlington. So he's very well educated and very well innovative person as far as I know him from the business perspective. And I'm happy he took the action. And then he is participating in our webinar series. And now, please, Vassilis, share your presentation.
Thank you so much, Katerina, for the introduction. It's a pleasure to be here and to share our work. Today, I will present how we tailor composite performance at the nanoscale, and more importantly, how we translate nanotechnology into real industrial composite applications. So I will start from who we are to how we use the nanofibers, how we actually process them into intermediate products, and finally how this translates into performance improvements in composite materials. First of all, let me say that we started 10 years ago, actually. It's been 10 years since the fall of 2016. AmaDema started as a small, like a startup in an accelerator. And since then, we have grew to a small group of companies. We have expanded to Greece. We have several production capability in composites as well as in textiles. So as I said, we started in 2016. We graduated, let's say, from this accelerator. And then at that time, it is when we actually started our collaboration with Elmarco. We did a visit in Liberec. We did the first trials of our NanoWeld technology there and found out how we will scale up the technology. Until that time, we were having a very close collaboration with, from that time actually, and until when we purchased our equipment in 2020, we had a very good collaboration with Elmarco that helped us backing up us in the projects that we were actually gaining into delivering to our customers and to our projects. We started working with European Space Agency projects in 2019 and 2020. And then after that, we started growing, increasing the capacity of our machine and producing more and more. Eventually in 2022, we started being in more fairs worldwide about composite materials, but not limited to, and growing significantly until today, where I'm actually, I can in 2026, we have currently strategic investors within AmaDema. This is an accomplishment of the first semester of 2026. And from that point and on, we invest significantly in expansion of our capex, of our production capability to cover composite materials demand of our customers. Here is a little bit of who our clients and partners are so far from different parts of, from different fields of applications, as well as suppliers and partners and academic and institutional partners. And let me start talking a little bit about AmaDema. So basically, we have three main activities. The first activity has to do with enhanced textiles. In enhanced textiles, we have the NanoWeld enhanced fabrics. It is our core technology, includes, of course, nanofibers. And I will explain a little bit more about that. So we use nanofibers to enhance technical fabrics for composites. This is basically what NanoWeld enhanced fabrics is. We also provide nanofibers for composite manufacturers that they want to use directly nanofibers without being implemented or combined with another technical fabric. And of course, we do the impregnation of those fabrics, which is with epoxy systems. So we create prepregs that they include the technical fabric together with nanofiber to be used again in composites manufacturing. So this is the first activity. The second activity has to do with composites manufacturing per se. And this is from the design, the engineering, analysis, prototyping, and manufacturing of composites. And eventually, of course, R&D services and grants related to composites and advanced materials. the first activity is what differentiates us from competition, let's say. We had to do all this, let's say, vertical integration into composites manufacturing in order to be able to commercialize the NanoWeld technology. Because the real problem, the real need is in the end customer, the end user, let's say. The end user has the need for stronger yet lighter materials, not the textile manufacturer or the composite manufacturer. So this is how we actually, in order to be able to satisfy this need, we had to start investing in more capabilities. So this is the impregnation machine, the electrospinning equipment, and of course a lot of quality control equipment in order to prepare enhanced textiles for to deliver enhanced textiles for the different applications. But let's see how NanoWeld works. And so the real problem in composites is the lamination. The lamination is caused from different ways and different reasons within the material when it's under load, and basically is the crack initiation and then propagation within the interlayer that makes the material to be defective and eventually to fail. So how we came up with NanoWeld? We got inspired by fractal structures found in nature, such as the feather. And as the feather goes from the rushes to the barb and then to the barbules, we basically go from lamina to lamina. We inserted those enhanced nanofibers in the interlayer, going from the fiber to the nanofiber and eventually to the nanoparticle. This very well connected structure of the fabric, which is repeatable from lamina to lamina, transfers the load more efficiently than basically only with the fiber. This is a patented technology, and depending on the nanofiber type, on the nanofiber material, and the combination with the nanoparticles, it can increase mechanical performance up to 100%. And the mechanical performance can be different properties, I will explain later, which can be tensile properties or bending properties or fracture toughness properties. Now, how we do that? We actually have our NanoSpider that creates the nanofiber. We create the solution, and then this is also something that we have worked a lot, and we have done a lot of research in creating different solutions of different polymers. So we have, let's say, a pool of polymers and different nanoparticles for different applications. Then we do the nanofabric. On the next step, we insert the nanofabric on top and on the bottom of the main fabric under enhancement. So it can be carbon fiber, let's say, or glass fiber, or another aramid or bio-based, or name it basically, or filter media. And then we actually consolidate it with thermocompression and ultrasonic welding. There is a combination, we call it thermosonics. So basically, out of this process, the potential products, our products, are of three main categories. Plain nanofibers, that they can be enhanced with particles, or dry fabrics enhanced with nanofibers, like carbon fiber of different width. There is we can actually apply the nanofiber on any type of weaving, unidirectional, woven, twill, biaxial, and different also GSMs of fabrics, and eventually also the impregnation system. So an intermediate product that is already pre-impregnated with resin. This is quite non-trivial, because nanofibers, they are very porous. We can achieve the desired permeability, but the pore size is a tricky point that can block, let's say, the resin flow during the prepreg. So this needed from our side a lot of work and a lot of experimentation in order to find the appropriate resin systems that would be able to go through the nanofiber and basically wet as very well the carbon fiber bed or other types of fibers, similarly to prepregs that they do not have nanofibers. So basically, carbon fiber rolls meet the nanofibrous membrane that has been taken out from the electrospinning system. The assembly passes through the furnace to lower the resin viscosity and increase the tackiness, and the nanofiber membrane adheres to the carbon fiber surface via chemical bonding. Then we have a second compression stage that ensures the full consolidation, and eventually the enhanced prepreg is rewound and stored. Now here, it's good to mention that we provide nanofibers attached to the main carbon fiber bed before it's impregnated, so impregnate with those resin systems that we have, let's say, optimized. But this means that it's a new prepreg system for some manufacturers. So it's not easy, let's say, to penetrate the market. What we have done, we have taken prepreg systems that are already in the market, that people or companies are familiar with those, and we can basically, for very specific nanofibers, we have basically made that we can process the prepreg and attach the nanofiber on it without losing the properties of the nanofiber and still have the nanofiber in the interlayer. Now, there is a difference between the two for those that they understand the composites, that when it comes to carbon fiber or other technical fabrics, before they get wet with the resin, they do have a sizing around the fiber. So when we do the NanoWeld on a dry form, the nanofiber adheres to this sizing, making the low transfer mechanism that I described before much more efficient. So eventually we have better properties. But if we want to use a off-the-shelf prepreg system, this connection with the sizing is not there. However, we still have increase in the final properties. Here you can see some different types of NanoWeld systems. You see how it looks like in a dry form as well as in a prepreg form on the right. In both of them, we have a unidirectional fabric, carbon fiber. Here you can see some performance in a qualitative and general form, comparing, let's say, in aerospace applications, metals with current carbon fiber composites and NanoWeld carbon fiber composites. And we can see how the performance can be increased up to 100% compared to current carbon fibers. We can have a reduced weight because of the better mechanical performance, we can use less material for the same mechanical performance. And of course, through that, we can achieve better fuel consumption and lower carbon dioxide emissions. So this part of the presentation was mostly about the enhanced textiles. As I said, we also have the design, prototyping, and manufacturing of composites. And of course, through that activity, we promote our materials in order to be used in different applications. It's worth mentioning here that those materials that they are used in such applications, they need finite element analysis in order to eventually optimize, let's say, the use of in the composites. And we have already done all the necessary testing in order to provide to the customers the FEA necessary, let's say, values in order to have optimal models. So we have used the material in drones, in drone structures, in electronics casing, and as well as in satellite components, small satellite components. And of course, this is about the research and development. So let's see, let's go more into the nanofibers now and how we prepare them in order to be used in the composites. We have 4 main steps. Is the selection of the appropriate polymer, additive, and solvent. Okay, I guess most of you that you're working with nanofibers, you're familiar with that. However, what really makes a difference here is to get the right, the appropriate, let's say, nanoparticle, depending on the application, and of course, to find the necessary, the optimal concentration. So we prepare solutions at optimal concentrations as discussed. This has to go through an experimental process. So far, for different applications and for different nanofibers, we have, as I said before, a pool of different, let's say, recipes. So we have done a lot of experimental work, which we can use for our customers. But of course, here we have also the expertise and the know-how to do further material combinations depending on the needs. We ensure the proper viscosity and conductivity for the smooth electrospinning and dispersion of the additives uniformly. And then after that, we have the normal electrospinning development process in order to find out the necessary parameters, depending again on the materials that we have selected above, and eventually do characterization with scanning electron microscopy mostly, mechanical properties in plane tensile strength and elongation. We have a very sensitive head for UTM for the mechanical testing, and the functional properties, conductivity, porosity, permeability, and biocompatibility, and additive distribution. So we need, let's say, all these properties, and we actually provide all these properties with technical characteristics of the nanofibers that we create. You see a little bit here an analysis of the previous slide. And now in different applications, we have components for aerospace and defense applications, that we have an increased stiffness and tensile strength. We have or other types of mechanical properties such as damping improvement, and also a specific application on that. We have some energy and electronics applications, high-performing nano-enhanced structural supercapacitors. This is a project that is in low TRL, but it's something that we have been working a lot with some partners across Europe in order to basically create a prepreg that can be used in structural supercapacitors in the future. We have been working with a specific application on filtration for oil and gas applications with super hydrophobic nanofibers. Also with advanced nanofibers for again with optimized with nanoparticles for sound insulation, and also for agricultural applications that we have biodegradable nanofibers with, again, particles that they are nutrients possibly to the plants. And eventually, one last project that we have is about biomedical applications with nanofibers for cosmetics, for cosmetic applications. In general, As I said, our main activity is in composites, but we have a lot of demand for nanofibers that they can have other functionalities and to be spun in different substrates. So let's go a bit more into the composites. I will do a very brief introduction to the basics, so everybody can understand the composite applications a bit better. So composite materials consist of two or more distinct materials combined to achieve enhanced properties and performance, usually the reinforcement and the resin system. So we have composite materials that they are in nature, such as wood or cellulose fibers, that they provide mechanical strength, while lignin, for example, acts as a natural binding agent. In fiber-reinforced composites, we have mechanical performance that can be tailored through the orientation of the fibers. This is the engineering, of course, of the composites, and this is what we achieve with the finite elements analysis, with a polymer resin matrix according to the operational and loading requirements of the structure. And this versatility makes composite materials ideal for a wide range of advanced engineering applications. Now, the traditional materials such as metals are isotropic with equal strength in all directions. In composite materials, the matrix, fibers, and fibers architecture can be engineered to carry loads in specific directions, and a capability difficult to achieve with metals. But this also has a lot of benefits in the structure, such as the lightweight nature. This enables thinner, lighter structures, as we said, and the resulting weight reduction improves performance and reduces environmental impact through lower carbon emissions. So fiber-reinforced composite systems have structural fibers encased within a resin matrix, as we said, a defined ratio, depending on the application. The fibers bear the structural loads. They are the main load-bearing structure of the composite. So the resin surrounds, protects, and binds together a cluster of fibers, and its primary role is to transfer the load through and among the fibers. So fabric and veils come in a variety of forms and ways. So in the case of the NanoWeld, we have the reinforcement, the carbon fiber or any other type of fiber, together with the nanofibers in the form of the veils. So the goal is to produce lightweight, corrosion, fatigue-resistant, damage-tolerant structures, cost-effective for different applications. So we reduce the weight, leading to reduced fuel use, fewer emissions, and reduce whole life costs, ability to produce large monolithic parts and complex curved structures because of the resin and the processing that allows this, larger, more integrated structures and reduced part count, sort and assembly times, reduction of fasteners through co-cure, co-bond, and design optimization, exploitation and the tailoring of material properties, improved fatigue life, reduced creep and creep rupture, improved corrosion and wear resistance, low coefficient of thermal expansion, and other characteristics to increase the product life. And eventually, to obtain smooth surface for either cosmetic appearance or for aerodynamic profiles. So again, going deeper into the NanoWeld, the interlayer reinforcement NanoWeld is an interlayer reinforcement via the electrospun polymeric anchoring nanofibers that we described before, that basically transfer the load more efficiently. It's inspired by the fractal structure, and it's a scale geometry from lamina to lamina that allows this higher performance. And in a different, of course, it can be used in different applications. So here you can see some sandwich panels that we have made for different structures in space applications. And let's see here we have different PVDF-based and PAN-based nanofibers together or plain or with carbon nanotubes. And you can see how the process of the prepreg was done in order to use them in different CFRP composites. So DMA, dynamic mechanical analysis, was used afterwards in order to evaluate the viscoelastic behavior of the nanofiber interlayers at CFRP level. So basically the CFRP performance with and without the nanofibers. Samples are subjected to controlled oscillatory loading. Key parameter is the tan delta as well as the energy storage. And then we have the phase one where PAN and PVDF nanofibers as interlayers are examined and seeing the effect on storage modulus and damping, the tan delta, and then optimize nanofiber with and without the carbon nanotubes, the effect on mechanical performance. So here a little bit, you can see how the control is here, the blue line, and then how we go with the PAN without nanofibers, without nanoparticles, sorry, is the PAN 2, 4, and 6 in different concentrations, going in above, let's say, the control. The PVDF, because it's a different polymer, goes a bit below, but gives a better toughness overall. And then we see how the nanotubes within the PVDF increase compared to the PVDF alone and go beyond also the control. And this is the storage modulus at, let's say, around 35 degrees of Celsius. Similarly, you can see the tan delta analysis, and you can see that the PVDF together with nanotubes exhibit a much better behavior, damping behavior, compared to control specimens. As a matter of fact, the control specimens are all the way to the bottom of this line, and all other specimens are above, either with or without the nanotubes. Now, let's see specifically for another component, carbon fiber component, that is in collaboration with Airbus Defence and Space and is designed for applications in space launcher structures. Here you can see that the control compared to the NanoWeld and the NanoWeld after processed with, within TVAC examination has a significant increase in the tensile modulus as well as in the transverse tensile modulus. This increase is quite significant and includes also the deviation. So especially here, we can see an increase up to 33%, which is quite significant for the aerospace applications. Another very good result here is the improvement to moisture uptake. So we have a 20% better moisture uptake, not uptake, let's say, compared to the control with the presence of the nanofibers. And this actually makes the this material, this prepreg material, suitable for the launcher structures that they carry liquid fuels. And you can see here, compared to the control and the NanoWeld system, how differently basically is the diffusion reduction. So basically the nanofiber-enhanced composite absorbs less moisture. This is our team, co-founders team, Vassilis, Katerina, Vassilis, myself, Katerina, Ioannis, and Evelthon. Our management team, Ioanna, Savas, Yanis, and Haris. We are a team of 16, 17 people. We are happy to talk more about our technology and our technological products. And I would like to have another couple of minutes to show this video that shows the vision of AmaDema.
As humans, we've always aimed for the stars, been desperate to get off the ground, race through the clouds. Our ambitions and dreams have known no bounds, never giving up, pushing to go further, faster. We've challenged physics, but there have always been limits we couldn't overcome. To keep going further, we had to be heavier, use more energy. More weight meant stronger. Stronger meant more energy consumption, more polluting. Once again, we ask, why? Why can't stronger mean lighter? Go further with less. Store instead of consume. And now we have the answers. At AmaDema, we're developing the next generation of multifunctional carbon fiber composite materials that can revolutionize the use of advanced materials in smart structures, transportation, and beyond. Enable energy storage, reduce weight and emissions, increase strength, and introduce innovative advanced features. AmaDema, unlocking the potential of advanced materials.
So yeah, thank you again for a very impressive talk, and I think it's going to be a big challenge on everybody of us to at least think about or consider nanofibers to be actually part of the composite. And then the video showed that this composite can be used as any kind of transportation, any let's say application where there is a need of lightweight and very strong material. So let me open up the Q&A session. And whoever has a question, please write them in Q&A session and we will answer them one by one. So I go right away to the first question. So what is the question is, what is the GSM range of nanofiber web used for aerospace and filtration and uses a minimum and maximum GSM possible? So this question is related to the overall thickness, let's say, of nanofiber layer, which you, Vassilis, has been demonstrated also during your presentation. So if you can cover that, please.
Sure, certainly. So it really depends on the application and on the property that we have to tackle. So let's say if we need higher fracture toughness, we need higher GSM in the composite. If we need a higher stiffness, we need lower GSM. Now, the GSM range is usually from 1.5 GSM up to actually 6 GSM, I would say. It in some cases can be a little bit more than that. So it depends on the application. And I think you also asked about the filtration, right?
I mean, the question, it was more like, I think in general, like, yeah, filtration, but also the thickness, general thickness of nanofiber layer you use in a composite. For filtration, I think it's gonna be less, right? For filtration.
Yes, yes, right. It's right. Yes, the filtration is right. Is less, but in general, the thickness in the composites is from 8 to 20 microns, no more than that.
Thank you very much. And I can actually say that this is very good number because, as you know, the nanofibers are lightweight material, so actually they don't weigh much. So typically, I mean, this GSM around 5 and 6 is kind of optimal, I would say, for the membranes in whatever sector you look. Yeah. So I think that your choice of selecting such a GSM for your product it's I think optimal and very good. So let's go to another question. The capacitor application that you mentioned is being commercially made by NanoWebs or how it is? What is now the development stage or production of capacitors?
Yeah. That's also a good question. As I mentioned in the presentation, is in a low TRL, in a low TRL, so it's not in the market yet. It's something that we have been developing the last couple of years with experts in supercapacitors. We are experts in the material part, and I would say that we have very promising results, but we need some more time on that. And I would say that the TRL development is currently around 4 to 5. So we have done the experimental part. The thing is the scaling, and this is the point that we are right now.
Thank you. There is a voice from audience. Thank you very much for your nice presentation and asking about possibility of sharing. Of course, we will share. We will, record. It's been recorded, and we will definitely share. You will see posted the whole presentation of Vassilis on Elmarco YouTube channel, and or you have a chance to contact Vassilis directly. Don't worry. One question from myself, maybe. So you mentioned incorporation of, let's say, nanoparticles into nanofibers. So how that is working? What is your experience? Because that's actually a very frequent question also from our customers. For example, if you can mention maybe the size of nanoparticles that you're working with, and how do you incorporate the particles into fibers? So what is the, let's say, ratio in concentration of particles and raw material, like a polymer, in your solution?
That's also a good, a key question, let's say, because when it comes to nanoparticles, you cannot really use the nanoparticles that you could potentially put in the resin system. The number of nanoparticles is smaller. However, it's in a more controlled environment. They are nanoparticles that they are within the nanofiber system. So the amount is much less. We can say that we have nanoparticles between 1 and 3, between 1 and 4% within the nanofiber. So basically on the nanofiber concentration. And the size, now it depends on we have been using nanoparticles such as clays, oxides, nanotubes, graphene platelets, which are quite big. But always we can see that also the size of the nanofiber can depend, let's say, on the type of the nanoparticle. We cannot go beyond a certain level because we start having a saturation effect, and then the nanofibers can be fragmented while the manufacturing. But it really needs some time to do that with experiments. So this is why currently we are working on an AI-based platform that we can actually optimize the nanoparticle reinforcement with depending on the application.
So do you buy the nanoparticles commercially, or do you make them somehow, or to collaborate with maybe third party?
Yes, we buy them, of course, from different suppliers, but we also collaborate with some local universities that they can actually use different processes in order to create nanoparticles.
If you can compare, and I think you had it also in your presentation, you had a composite made of a nano layer only, and then nano layer with nanoparticles. So would nanofibers layer only has a function, in that composite without actually nanoparticles? Yes. If you can compare it a little bit again.
Yes. So with the nanofiber alone, can create a crack propagation inhibitor. So basically it locks the crack while the crack actually propagates. It can meet the nanofiber and will have to decide, let's say, the crack will have to decide if it will go around the nanofiber or through the nanofiber, and this basically increases the flux toughness of the composite. When it comes to nanoparticles, we have an extra benefit, which is this anchoring effect, because the nanofibers tend to protrude from the surface of the nanofiber, creating an anchoring mechanism with the cross links of the matrix system.
Okay, I see. I have a question about the production actually itself, because that's quite interesting, and I'm kind of practical person. So how long does it take? Let's say if you can mention in maybe hours, or I know you're not really fully automated, or maybe you are already, but how long does it take like to produce the entire reinforced composite material, from, let's say, starting with nanofibers and going to, each step that you need to do, making some molds, maybe do some other operations. So if I will be your customer and asking for some part, some component, let's say for car or for, aircraft industry, how long does it take to process it?
So it's a good question, actually. This is something that has made us pivoting since the beginning of our operation. So in the beginning, yes, the customer, let's say, of the textile is not the end user, so the automotive industry, let's say, is basically who makes the components or who produces the fabric. So basically, this is whom we were targeting in the beginning. However, it was not so trivial when we started going out saying that we have this technology that does this and this and makes better fabrics. It was not easy to enter, because the problem is not theirs. The problem is of the automotive industry in your example, or let's say the end user. Could be aviation, it could be different sports, or name it. So yes, I will have to separate it then, depending on the customer. So if the customer needs a textile, then we are talking about hundreds of meters per day that you can produce. Okay, but when we are talking about components, then it's a different procedure. And when we go to production, we are talking about some tenths of products per week.
Okay, different sizes, right? Or what is actually the maximum size that you ever made with the nanofibers?
You mean as a composite?
Yes, like a composite.
It's I don't know, 4 by 5 by 2. It's a big marine project that we had to do. Yes.
Yes. Correct. Oh, that's quite huge.
Yes, it's big.
Question from audience. So the question is, maybe you already mentioned, but what polymers do you mainly use for making nanofibers for the composite? What polymers?
Well, we have a big, as I said, we have a big pool. So it's not, let's say, if we say that we do PA6, for example, it's not just PA6, it's a PA6 with different particles. So each one, it's a different system. Mainly we use PA6. We start with PA6. We have been working with PAN, PVDF, you can see also in the presentation. But also we have gone to bio-based resins. So it's a pool. We have also worked with PCL, with conductive polymers, like PANI. So there are several polymers that we have been using in order to also very high dense polymers. Yeah, so it's a quite big pool. Yeah, depending on the application always.
Okay, thank you. Another question. So what was the application of the composite for space application? So what sort of testing did they go through? So if you deliver, or somebody is requesting the composite for the space application, what do you need to measure to prove the quality, let's say, of such a material?
Well, in the last project that I actually presented with the launchers, we use the material system that has already space heritage. So we took a prepreg that is already used in space. So we took this material and we applied the nanofiber on top of it with a special processing process, of course. And eventually this was used, and you saw the results that they presented. So in that case, the testing is quite, although the material has some heritage, let's say, it's quite intensive. So you have to go through different phases. So at a coupon level, and then at a monolithic level, and eventually at the component level. When it comes now to materials with non-space heritage, this is even more intensive. So yes, it's not easy to get into materials for space, but as soon as you get there and you get some customers that they have a reputation, then the whole, let's say, system works to adopt new materials.
So do they provide the measuring themselves, I mean your customers, or you need to do some measurement in tensile strength or some like hardening, qualification of the, let's say, strength of the material some other way, or how do you deal with the quality, let's say?
Yes, the quality, that's also a good question. This is the quality has to be done by accredited laboratories when you're talking about space or aeronautics. So it's not something that we can do in-house unless we have, let's say, an accredited laboratory in our premises, which is not the case because you need a lot of equipment. So usually we have to go with those guys that they actually have the necessary equipment, and this is quite expensive. It's an initial investment. We, thank God, we had the grants in the beginning to help us with that.
Yes.
And then, of course, we could use the testing results. But then, as soon as we get into some projects in space, especially since we are talking about space, we had available budget for further testing at this level.
Thank you. And maybe one of the last questions, since time is going very quickly. So the question is, first I like you to answer, but maybe I will add also something from my perspective. So question is related to the production speed of nanofibrous webs of PVDF polymer on the carbon fiber based fabric. I don't know if you, I haven't really noticed in your presentation if you are using carbon fiber based fabric and then you coat it with PVDF. Please comment on that. And the question is about the production speed.
Okay. Okay. So I will start because you said you want to mention something, but maybe you can do after.
Yeah.
So yes, we do carbon fiber with PVDF. Usually, the results that we presented here are not, the nanofibers were not spun directly on the carbon fiber, but they were actually consolidated on the prepreg later on. We have done also on the carbon fabric directly. In general, when we use carbon fiber as a substrate within the electrospinning, we need to use small speeds for safety reasons. But when it comes about the speed of the PVDF electrospinning, it really has to do with the desired GSM. So the higher the GSM, the slower the process. That's how it goes.
Yeah, exactly. That's what I wanted to comment. Yeah, because that's also related to the selection of machinery that you have here. We as Elmarco deliver different sizes. So bigger size of machine you have, more electrodes you have. So your production can become more productive by adding more wires. So, I mean, Vassilis will maybe comment the speed they do on their machine while they're having just one electrode. But, you know, we can add more electrodes into the row, so we can definitely increase the speed. And then it's nothing easier than to come either to him for the, let's say, request of production, or if that's related just to PVDF layer, maybe you can contact us. So that's That's about it. And the time is over. I'm very sorry about it. Questions are over also. So thank you very much for listening. I hope you stay with us. We're going to have a little break now with the webinars. We are coming back in September because we have other activities and summer is coming. So everybody is going to be enjoying the nice weather. And we will come back definitely September with very interesting topics. Thank you again for following us. Stay with us and keep spinning. Thank you. Goodbye.
Thank you.